Second good morning to you on this beautiful Saturday. Was it June 1st? So, ionizing energy, ionizing radiation, the word ionizing. What does that mean when you hear it in relation to high energy? Um, you've heard of non ionizing radiation, which is generally termed as lower frequency radiation. Okay, remember we've got DC voltage, which has no frequency, it's just the voltage and on. We've got an AC voltage that the power goes up and down and up and down, and how often it goes up and down is the frequency. So that frequency you hear of in hertz, very, very low frequencies. Elephants are actually thought to talk in these very low guttural frequencies. Whales and ocean mammals use low frequencies. Now, by low, I mean even in below our audio range. And we can only hear up to 16 to 20 kilohertz. That's 20,000 cycles per second. So these frequencies change. What I spoke to in another video is boundary layer physics, where you kind of step through one door and you're on the other side, and the rules in this new room are different, but the old room still exists. So you get into at higher frequencies, lower frequencies, DC voltage. We think about circuits in terms of resistance and impedance is discrete items like a choke or a capacitor. So all those devices together make a circuit that behaves very known at low frequency energies. When you get up into higher frequencies, the terms change. You go from resistance and capacitance and inductance you go into I lost my train of thought for a second here. So you go into impedance of circuits when the frequencies start to increase. As the frequency of the energy goes up, we're talking about electron energy now. Electrons that orbit around atoms. So iron conducts, copper conducts. It's got a lot of free electrons in the outer valence, so it's a good conductor. So the frequency of the energy is really what we're concerned about with higher frequency energies, more so than some of the voltage conversations. Again, this is we're in a graduate level area here, trying to poke at some of the pieces. So resistance changes into impedance as the frequency increases. So I talked about hertz in this very low frequency. This is how submarines communicate with each other and with us back on land, is very low frequencies, VLF. So that's radio or it's being used as a radio frequency, but it's a low frequency. When an elephant stomps the ground, it can be heard miles away by another elephant. Their feet are that sensitive to these subsonic vibrations. So this is energy. This is the ways you can talk about energy, it can get very confusing. So back to ionization. Ionization specifically is talking about moving electrons on an atom or on a large group of atoms. So we've got gas phases. We've got, again, these a gas has a frequency, which is very odd to think about because the molecules resonate. And here you go into some woo land that's actually some describable physics, but people will turn it there. So ionizing energy is energy to move electrons. That kind of is as simple as it is. Unless you go into a room that is talking about a specific type of ionizing energy, you can use these vagaries to play with the words, and you can make woo and fiction out of this and make it all mystical, and it just isn't. It is complicated. It is hard to understand, but it's not mystical, magical. That stuff doesn't exist, folks. So ionizing energy is something that's going to move electrons around, very basically. But truly ionizing energy is something that knocks electrons around instead of makes them just move. So voltage, potential, right? Current moves from minus to plus. So that plus voltage creates a potential. If it's a DC voltage, it's pretty straightforward. If it's a high frequency, gigahertz, the microwave range, radar ranges, which are overlapped and in the energy spectrums, can cause confusion in the conversation. So this was never going to be easy. If you expected it to be easy, if you think one equation is a problem out here, then you don't understand the equations very well. So that ionizing energy is more specifically meant to speak about moving electrons in shells, in atoms, or in a molecule, because electron bonding is one of the most common ways for molecules to hang together. Now that's chemical reactions, right? So you've got some deep chemistry. You can go into those equations, reaction equations, and do all of that. And some of that is ionizing energy just in the chemical reactions between two reagents, a base and an acid, or a hydrogen atom being mixed with an oxygen atom to create water. It's instant fire because of the energies between the two of them, and water comes out of it. So we get that. We're trying to harness hydrogen for cars, I suppose. Don't know if that's a good idea. So ionizing energy really gets very confusing very easily. We've heard conversations lately about two types of ionizing energy, and frankly, the conversations are really weak. You have to be more specific, and then you're writing a thesis and not a paragraph. So, ionizing energy, an argon plasma. Okay, a plasma takes radio frequency energy into a coil so that where all those waves wrap in the center is a super high energy magnetic field that shreds the electrons off of. First, it shreds any elements in the compound apart. So if you have H2O, out of that flame from an argon plasma, you will get a reading for hydrogen and a reading for oxygen. Because that energy is so high, it rips everything apart inside of that sampling system. That's minute amounts. It's parts per million things inside of that stream, but that's what we can measure. So that optical measurement relies on ionizing energy from what is basically a microwave antenna inside the cabinet. And it blasts everything apart that comes through the core of that little magnetic induction field and shreds it apart. When the electrons from that shredding cool and come back into their normal shells, they emit light. We measure that light. That's how optical emission spectrometry works, is looking for the light from specific particles and even from elemental binding, or compound binding, depending on how good you are with these things. So ionizing energy is such a broad field. Now you get into conversations about 5G. Is 5G frequency an ionizing energy? They call it non-ionizing radiation. And there is such a fine boundary between this and what it's ionizing and what it can ionize. So microwaves are ionizing radiation if they're in a high enough energy concentration. Period, end. Period, end. A microwave tower emits ionizing radiation energy levels. As it gets further away from the tower, remember that inverse squared power laws that work out here, that power decreases enough over distance that, big question mark, can or will this harm you? Can the resonant frequencies affect things inside your body that are coming off of that microwave tower? And the answer is yes. It's not a no answer. If someone says no, they are misrepresenting information. Because again, AC 60 hertz, that magnetic field, does energize things around it. But it is an energy that is basically so low, so basal, that it does not have any effect that we have been able to measure from that 60 hertz 120 volt line. When you get up to higher energy lines, all the rules change. There's 47,000 volts in high power lines. There's more than that, depending on what kind of high power line it is. Those are stepped down through transformers to 120 volts to come out your wall sockets. But that's how that large energy packets are moved around. Is that ionizing energy? A high voltage arc is ionized energy. It's a plasma. This is the languages inside of the sciences that when you start to smear them, it can make a mess. So this one's almost a 15-minute mess. This was a poor intro to ionizing radiation, and I tried to stay on topic. It would take 6 semesters, 8 semesters to step through the half that I do know. So on part of this, I'm not the right person to ask. On the other part, I might be. So keep ionized, folks. Keep your energies up about pollution. Thanks for listening.